Okay, hi everyone. To welcome to this week 9 problem solving session for the course of Introduction to Electromagnetic Theory in Hindi. So today we are going to talk about reflection and transmission of light falling on a dielectric materials. So here we will only talk about the normal incidence of light, and in that also we are going to talk about the transverse wave. Uh, So it's not like a longitudinal wave or something. We will be interested in transverse wave of electromagnetic radiation, and that is falling on a dielectric on the surface of a dielectric. So obviously, if the dielectric, so it has a different refractive index than the vacuum, you can say, or air. So at the boundary, what happens to the coming electric field that is being incident on the boundary, and how it is going to propagate in the dielectric media, and is there any reflection or anything. So we will be interested in that, in all these things, and we will be like deriving these things and solving some problems related to uh, the reflection, transmittance, etc., etc. Okay, so I think I will go to our first. Let's recall what is the Maxwell equation. So we know that there are four equations, which is del dot E is equal to 1 over epsilon naught rho, which is just the differential form of Gauss law that we have seen in the previous tutorial session. Then there is del dot B is equal to 0. So this has no name, but it means it essentially means the divergence of a magnetic field is 0, means there is no monopole, means whatever is going through some point it's also coming back, means uh, the net flow of the field is 0 through the point, through any point. So then there is the third equation, which is del cross E is equal to minus del B over del T. It's a Faraday's law. That means this is differential form. The integral form is that if you have a permanent magnet, and if you have a coil of wire, then you are moving that coil here and there with respect to with respect to the this magnet, which is fixed as some place. Then there is going to be voltage generating across the wires of the coil. Or otherwise, you can fix the coil, you can move the magnet. So it's relative effect. And the third thing you can do, you can change the field strength with time, and still you can get the voltage without moving anything. So this is how it's. So what happens essentially is that the changing magnetic field flux. Let's say changing magnetic flux, not the field. It's the effect of field and the area multiplied. So if the flux changes, which is field into the area, and if it changes, it can change due to the change in the area, otherwise it can be changed due to the change in the magnetic field V. So it changes, then it can generate a voltage, and that was the del cross E. So voltage is nothing but the voltage can be written as the gradient of E, and from there you can calculate somehow this. We can have this equation in differential form, that is del cross E is equal to minus del B over del T. And the fourth equation is the del cross B is equal to mu 0 J plus mu 0 epsilon 0 del E over del T. So what is del E over del T is the displacement current, which can be understood if you have a capacitor and you are applying some DC current. So if you make a cross section here, mean not the cross section, Gaussian surface here, so you can calculate some magnetic field. But here there is no magnetic field because this is a capacitor, there is no current. So how you are going to account for this current, this thing? Because there is a charge accumulation now. So with this thing was failing, means this equation del cross B is equal to mu 0 J, that was the earlier equation. So what not being satisfied, so Maxwell intuitively added this term del E over del T, that we call as a displacement current, where it also takes account of charge accumulation that is happening in the circuit. Means whatever current you are flowing in the circuit, if it is being accumulated at some point, so adding this term mu zero epsilon zero del E over del T will compensate for that. And the beautiful thing about this is that here you can see that the right hand side has electric field, which is changing with time, and it can change because there is an accumulation of charge. So charge give rise to electric field, and if the charges are coming and coming and coming and being accumulated, so that means whatever the field they are generating, whatever kind of field electric field they are generating, it is going to change with time. So here you can see the right hand side has changing electric field, but the left hand side has this magnetic field. So it's not only the changing magnetic field that generates the electric field according to equation 3, but inverse is also true that a change in electric field will also generate a magnetic field. Okay, so this was the Maxwell's equation in a vacuum. But if you write this Maxwell's equation in a media, so you know the displacement vector that is given by epsilon 0 E plus the polarization. So this is that D vector, displacement vector, and that is equal to the free charge density. So that is very like easy way to calculate some electric field at any given boundary, because you have to just only take care of the free charges. So in a medium, if you apply an electric field, let's say if a dielectric media, you apply electric field from this x-axis along this axis. So there will be negative charges on this side and positive charges on this side. So there will be a polarization. So these charges are induced charges, and they also will create some electric field. So what happens that if you are going to calculate this thing, like how much the electric field is there in the media, so you will be like you have to take care of the free charge, you have to take care of this induced charge, and if there is ununiform distribution of this induced charge in the volume, then you have to take also care of not the bounded charge but also charges that are in the volume, so volume charge. So all these charges you have to take care. But if you switch for this D displacement vector, so what you have to do, you have to just take care of the free charges that are there in the medium, nothing else. And you can calculate the displacement vector. Then del dot V is 0 as usual. And then del cross E is equal to minus del V over del T. So you have seen this. So that's it. Okay. But now the equation we are writing in terms of intensity. So what is the magnetic intensity H? Is essentially that. So what happens like a, in electric field, like in electrostatic, we can calculate the electric field by putting a capacitor, accumulating a charge here. So there is this electric field we can control, right? Now, if you come in magnetism, so what can you control is the only applied current to an electromagnet. So how much intensity of magnetic field you are generating, that is denoted by H, and what is the magnetic field is denoted by B. So that's why we have written this in del cross H, and that only take care of the only charge density J free. And what is the J free charge density? It's the charge density that we are applying, right? And then again there is del D over del T. So that is the displaced electric field. Okay, so this is the Maxwell's equation. And last class I told you about like how you can go through this equation and you can derive magnetic field. Sorry, you can derive an equation of electromagnetic waves inside a media or anywhere by using these four equations. So these four equations will give you an wave-like equation with the conditions that are there, and with appropriate boundary condition, you will find it out that they are kind of a plane wave solution. And if they are plane wave solution, so what happens now? Okay, so what we are going to do this here in this week is trying to understand what happens when a plane wave of electromagnetic radiation is coming and it is hitting a dielectric media. So what kind of a phenomena that are going to occur in this electric field? It's going to totally transmit, means uh, the whatever the electric field is coming here, it is going to transmit it totally this direction, or there going to be some reflecting back. So this is what we are going to understand now. So can understand this using this schematic that I've made. So here you have a incident wave that is just shown in red arrow. So you can see it's shown in a red arrow. So this is the dielectric medium. So this part, this is the boundary. This is not the media. This is the boundary. So I'm showing the boundary where the sharp boundary, and left to that means x less than zero. You have the epsilon one medium with the dielectric constant epsilon one, not the dielectric but permittivity epsilon one, and the second one is the medium with epsilon. Now, what happens in x less than 0? So here you can see our incident wave is coming at the boundary, and then after being it's being transmitted, and some part of this is being deflected. Okay, and we have chosen the permeability H mu 0 because we are taking it a non-magnetic media, so we don't have to take care of this magnetic thing. We are only saying that this is non-magnetic linear dielectric media. Okay. Now, so here we can see that in the reality, when light is incident on a dielectric media boundary, so what happens that there is some transmittance, there is some reflectance. So, okay, so it's not that the whole electromagnetic field passes through the media. No, there are there's something, some part of it be it's reflected and some part of it being transmitted. Okay, so with this understanding what we can, okay, so where we can see this, so you can see this in your daily life, like if you have partially, if you have mirror, so it reflects also, right, and it transmits some light but it also reflects some light. So this is how it's a simple mirrored dielectric media, so you can see this there. Okay, now what we can do with this, we have to like understand. So our first question is write down the reflectance and transmittance for normal incidence of a wave. So what are the reflectance and transmittance? So how much that like how much electric field is being transmitted and how much electric field is being reflected will be like uh, with respect to the amplitude of the incident wave, that will give you some coefficient, and that will be your reflectance and transmittance coefficient. Okay, so let's do that. Let's solve this. Okay, let me grab my tab real quick. I will share my screen. So I think you can see my screen now. So our question was like, what is the reflectance and what is the transmittance of a normal incidence of a wave on a dielectric medium? So we have this epsilon 2 here, epsilon 1 here. Okay, we have some incident wave, some transmitted wave, some reflected wave. Now, so as I told you that we are only interested in the transverse uh, electric field or magnetic field. And since we know that from previous tutorial session that uh, the waves that are being EM waves has this plane wave solution, means that they are like some A sine kx minus omega t kind of thing. Okay, so this kind of waves that we are expecting, so we can write down here for the medium one. This is the medium one. This is the so mu zero. What else? So let's say that the incident magnetic electric field is I, and the transmitted is T, and then you have the reflected one ER. Okay, so these are the fields. Now, okay, so what is the propagation direction? You know that last time we have this field equal to the direction was. E cross B, right? E cross B. This, there was some constant, I think. Yeah. So it's no, no. This was the pointing vector. Sorry, this was pointing vector, and it switch in which direction the wave is propagating. And it also it is same with the propagation vector k. They are pointing in the same direction. Now what we can have is this actually the k vector was okay, the k vector was k cross e. This was the k vector. So this is the this is your velocity. So this is the magnetic field. Means this can be your velocity if you normalize this, like you take out the amplitude. What I'm going to say is that this can be like this. Okay. This is that. Now, so we have, let's say we have the incident wave. So we have EI, that is G, EI, vector sine kx minus omega t. So this is the x direction. This is the x, y, x, y, and g is x. Okay, so this is x, y, and g. Now we have this incident field. Now we have this reflected one. We can write also, but let's write for the transmitted one. So PET will be transmitted 0. And this is also going to be sine kx minus 130. Now, so where what is I 0? I 0 vector is nothing but some amplitude of EI 0 x cap, and ET 0 are nothing but ET 0 y. Okay, so these are the vectors that we have. Now what we are going to do, we are going to calculate something. So we know that from, okay, so why I told you about the Maxwell's equation, reason was this, that let me write down the Maxwell's equation first. So we know that at the boundary here, there is no current, J is 0, rho is 0. So we don't have to, like, we can write this as this, this del dot E is equal to 0. So it should have been rho upon epsilon naught, but there is no rho, right hand side is 0. Dot B is 0. So third one I'm writing is del cross C, that is Faraday's law. Del T, that is also there. And the fourth one is del cross B, J. So J is 0. Okay. Now what we have to write? Uh, so we know that, okay, so what we have here? We have this electric field. This is the propagation direction. So at this boundary, we have the electric field and magnetic field. Okay, so what can be the, okay, so the transverse wave means the propagation direction k and the oscillation direction. They are perpendicular. Means k vector is x cap direction, and the oscillation that are happening in y cap, and that is for the electric field. Electric field is y cap. Okay, the electric field vibrations are in the y cap direction. Okay, so now what we have to do, we can write what we can do. Let's say this is the electric field here and here, and this medium one and two. So what you can see, you uh, make a Gaussian surface parallel to this across the boundary, and then make it go to zero. Like this Gaussian surface, this had to bit the delta from here to here. So 10, 10 this delta to zero. That means this will box will be like zero area. So right now, let's say if the whole thing is like this is 2 delta, 2 delta, and this is let's say A. So the area is you have 2 delta into A. But if you take the delta going to zero, that means the area will also go to zero. Okay. Now keep this in mind. This is the electric field component in the medium one. So this is the parallel component. So you can have one parallel. Okay, so you know that del cross E equal to minus del B over del T. Okay, so using this equation, what we can do, we can have del dot E. So this can be written as E dot D some that is C. So this is the loop. You can write E dot DL across this, and if this is so, so it can be minus del B over del T to DA. You know the theorems where we change this. Okay, let me write it down. Del cross E is equal to, if you take area integral of this, so you can write this as E dot dl. So Stokes theorem over a curve, right? The curve, surface, sorry, this is the surface integral, closed curve integral. So this is the closed curve integral. So this is what we are doing. We are taking closed curve. So if the both are like the electric field in parallel components are like this across the boundary. So what will happen that if you go from like this way and this way. So here the both the DL and the E both are in same direction. They go this way and come back this way. So here DL and E both are in opposite direction. So based on that, we have E1 parallel minus E2 parallel. Okay, E2 parallel equal to, and this is what you can take out the del B over del T. But this is B dot dA. Now what we have done essentially that there is some uh, finite L that was A. So this is this, but here you can see if you have this del D under del T, but small area element will be area element is strip. Here it can be A into delta very small, so that will be A into delta, but this delta is going to zero. So this whole right hand side this whole thing goes to zero because this area is going to zero. And if this is the constant, so this must be zero. So that means E1 parallel E2 parallel and it could be zero. This is our one condition that we have found at the boundary. Now what is the second condition? So we know that the fourth equation is this del cross B uh, not del E del T. Okay, so similar way we can if, if we can think about can think about the electric field like this way. So because the k vector is because the b vector, because the b vector is perpendicular to k cross e. So if that was the e vector and the k vector is here, so k and e, so this will be like k and the e vector, so it will be like coming out of the plane here. So this is the magnetic field direction. Now what we can do, we can make a okay. So okay, so this is also the electric field. So magnetic field will be like this also. So this is the k vector. Now what you can do, you can make a Gaussian box here, the in plane or in the parallel plane of this magnetic field, the electric field. Now what we have, you can also write this from Stokes theorem. This can be written as dot E integral epsilon E over del T into dA, right, over the surface. The surface is this one. So what we can have is that B parallel, B1 parallel is equal to B2 parallel. Okay. Now, if we see about this, so that this is the boundary conditions that we have. This is the equation second, this is the equation first. So let us write down what we have. First was the condition, first condition was condition one, or that E1 parallel should be equal to E2 parallel. This medium one, whatever the medium one has the magnetic field, sorry, electric field, this has to be this. The second condition was that the magnetic field parallel components are also equal. So, okay, this now we know that it should be k cross e. Now, if I change, okay, so this is for the this is the incident wave and this is the transmitted one. So incident is the is like this and the transmitted is the same direction transmitted. So if the electric field of incident is in y cap and this is transmitted a vector, it's x cap, and the b vector is z cap. So is like this e vector. This is the wave vector. It's in z cap direction. And this is the k vector, which is x cap direction. Okay. So k vector is the propagation direction. Now what happens? So this is for incident. This is for the incident and the transmitted. Now what you can do, you can just also visualize this like at the same time. So when you have this that interface, now you have the electric field in this direction, both sides. Now you have the magnetic field that is perpendicular to this and perpendicular to the propagation direction constant. So let me make this coordinate system also. So this is z, this is x, this is y. So this is how you are treating this. Now, if you assume, okay, not assume that if the wave is reflected back, so your k becomes k goes to minus k because this is being reflected, right? This is the k direction. So what happens to your e? So e remains like the same, but b changes its sign from positive to negative to satisfy this because if you are e in e has in okay b should be, let's calculate the direction of b. So what happened to k? K become minus x cap and you have to k cross e, right, times if e is y cap. So what happened to b direction? Direction of b is direction of b is minus g cap, right? So means that this is switched this direction, and that's why if you now think about it, so what is the total components of electric field E? So this is the incident E I, and this is the reflected E R, and this is the magnetic B I incident. Oh, sorry. Okay, component we are writing, same direction. So this magnetic field has reverse. So that means it, if you think about it, the z direction, cap direction. So you have to take like minus r reflected. Okay. So this is the incident and this is the reflected. Sorry, this is the r. Here the here it's in the same direction. So transmitted, E transmitted. So it's okay. Now what does it mean to have a parallel component equal? From first condition, we have left hand side the total parallel components of the electric that are E incident plus, because they are in same direction, so that's why they get be summed up. ER is equal to E2 parallel. What is the E2 parallel? Total electric field in the second media. So that is E transmitted, right? E transmitted. Now the second thing is we have the total magnetic field. So P incident minus, because it's reversed, so that's why minus sign. Total will be the, like subtracted one. VR is equal to what? E, sorry, P transmitted, right? Total magnetic. Now from here, but we know, but we know that E is equal to P is equal to E mod of E, a mod of phi. So phi is the velocity in the medium. So the equation, this is the A and this is the B. So if you have EI plus ER is equal to ET and BI minus BR equal to ET. So you can replace this one. If you have you can use this in this equation second. So that means this equation second, this remain as it is, but this one will change. So it will be like EI over V1 for the velocity in medium one minus ER V2, and then you have this ET over, oh sorry, not V2 because this same area, right? One. So this is the new equation. So equation EI plus ER is equal to ET plus EI over V1 minus ER over V1 ET over V2 is equal to 2. So now if you solve the R comma ET in terms of E incident. So you have two equations and ER and ET. Sorry, let me write it back. So EI. So you have ER, ET, two unknowns and two equations because EI is known. We know how much light we are sending, how much electric magnetic wave we are sending. Okay, so we can solve this. So multiply, divide both sides with equation 1. So EI over V1 plus ER over V1 is equal to ET over V1. So what we have is we have also equation 2. So EI over V1 minus ER over V1 is ET over V2. This is equation 1. This is 2. Now just sum it up. So you have this AI and you have ET, and that ET is now have this common 1 over V1 plus 1. Now you have to think about it like the ET will be twice of, so you can think about it like this ET. So first let's simplify this. So it's twice of E1 means E incident, sorry, over VI, V1. This is ET transmitted. So you have V2 plus V1 over V1 into V2. Now you can cancel out the from. So you will have, okay, you will have now E0. So whatever the transmittance being done, it will be like 2 over 2 plus incident. Okay, so this is what you got. Now, this is saying something. Like if you know the velocity in medium 1 and medium 2, after you have sine a light, okay, so you will know how much means this is, if you say this is 1, means it is 1, its amplitude is 1. So you know there is this V2 plus V1 is going to be greater than twice of V2 if the medium is changed. So that means not all the light is being transmitted, some light is also being reflected, and that you can calculate from this equation one also. Here it's there. So you can calculate the reflected light. So ER will be because this was this EI plus ER is equal to ET, right? This transmitted one. Now what we did, so we have ER is equal to ET minus EI. Now that means that ER will be twice of V2 over V2 plus V1 EI minus E. Okay. And if you take out the AI common, so you have 2v2 minus v2 minus v1 over v2 plus v1, and then you have this AI. Yeah, so you can see that uh, the reflected will be v2 minus v1 over v2 plus v1. So this is the total reflected amplitude, like how much it is going to be, and how much it is going to be reflected. Okay. Now so this is the coefficients that is a reflectance, and this is the transmittance. Now the next question is, so the next question is next question is write down the energy carried by the transmitted and reflected waves. So we have to calculate the energy that is carried by the reflected. So we know, if we know the field E in anywhere. So what is the energy? Energy density is U is half epsilon naught. But the energy that is being carried in time is given by this S, average of S, is a Poynting vector. That is the energy density multiplied with the velocity. Okay. So you have this. If you are talking about the reflectance, so here is the transmitted ET with velocity medium in medium 2, is V2, and the reflected one in the medium 1 has velocity V1. So like this. So you can have E1, okay, this is E1, so it's E reflected. So you can calculate this S reflected for reflected. You have this V1 and then this density that we have epsilon naught. This is because the vacuum, so you can write epsilon naught E square, E reflected square, and the velocity here is vacuum. If you say so, otherwise you can write it epsilon for the media one and the velocity that we have already written. So this is going to be the energy carried by the heat, and this will be like the transmitted one. Transmitted will be like V2 of epsilon epsilon 2 transmitted is one. So this is the next question, and we have written it down. But we have to just only know the amplitude. So we know the amplitude of ER and ET square. That is, we can write. So now we are being asked what is the reflectivity and the transmittivity at the interface. So we have seen that uh, okay, we have seen how we can calculate the energy density at the interface, and then we have also seen like how we can calculate the how we can calculate the this energy that is being carried. So first let me define what is the reflectivity and the transmittivity. So reflectivity and the transmittivity are the ratios of this power that is being carried by this electromagnetic wave, the reflected or transmitted uh, waves. Whatever the power these waves are carrying, and if you take out the ratio with respect to the whatever we are giving, means the incident wave. So that will give us the coefficient of reflectivity and the transmittivity. Okay. So now continuing to this previous one, we can write down the question number three, that we have to find out what is the transmittivity and what is the reflectivity. So transmittivity means how much is being transmitted and how much reflectivity is how much is being reflected at the interface. So how much with respect to what? If you ask this question, so answer naturally comes like whatever we are incidenting, right? So whatever the light is falling at the interface, so how much part of it is being reflected and how much part of it is being transmitted with respect to that. And what do you mean by respect to that means you can take out the ratio. So if you are giving one watt power, so how much is being reflected? Zero point 0.5 watt, and that means that zero point 0.5 watts would go if the electric medium is not lossy. That's a different thing, but this is how you can understand. So this is so now we knew that the SR reflected one was the velocity in 1/2 epsilon 1 ER square, but we know that from the previous question that ER was I think V2 minus V1, right? V2 minus V1 over V2 plus V1 and the incident electric field. Now, if you calculate the square of this, so it will be E square, and this will be like V2 minus V1 over V2 whole square, and it will be like EI square. Now, what you understand from this is that if you put it back here, so it will be like 1 by 2 epsilon 1, and then V2 minus V1 plus and then EI square. So this is the SR. But if we are talking about this, so let us calculate how much intensity is there, the like how much we are giving, how much we are putting, like what how much intensity we are sending the incident wave, right? So that will be S incident. So what it will be? It will be the velocity of it, that's V1, and what? And it will be the energy. So energy density that is G incident. So it will be like P1, and the energy density is half epsilon naught. So not epsilon, epsilon 1 E incident square. Okay. Now what I said that the reflectivity is defined as if you take out the ratio of SR, the power that is being reflected and the power that we have incidented, so you can get it. So V1 half epsilon 1 V2 minus V1 over V2 plus V1 square I square over V1 half epsilon 1 EI square. Now, if we calculate all this, so you have this V1 will cancel out with this one, half will cancel out with this one, epsilon will cancel out with this, will cancel out with this one. We will be left with V2 minus V1 over V2 plus V1 square. This is the reflectivity coefficient that you are looking for. Now, okay, so this is the reflectivity coefficient. Now, what you can do with the uh, transmittivity coefficient? So for that, we have to do the same thing. So such the same thing will be like the same thing you see for the transmitting one, that's the E0T. So you can do that also. Transmittivity will be S S transmittivity. So it will be because we knew that it is this much. So it is this much. It is this much. Just keep this in mind that it is this much. Now, so if we are going to calculate the ST, so we have to just because we know that ST is nothing but the coefficient, sorry, the velocity, uh, transmitted density. Transmitted density will be like the electric field in that medium is equal to means ET or epsilon and this is square. So we know that we can write this in these terms. 2 half epsilon 2 for the medium. It is 2v2 and then you have this I. Right? Now if we take out the ratio, so for transmittivity, if you take out the ratio of ST over SI, so you have this 2 1 by 2 twice of I square over what? Over the that is incidented of this half this thing and then on one have this, then you have this EI square. Incident cancel out this half, not this one to cancel out. So you have and the square of this. So you have like and twice of like square. Now what we can have uh, because we know that this N1 V1 is also that means and where N1 is under root epsilon 1 epsilon 2. So this is how we can write. And if this is the case, so what does it mean? That means that epsilon 1 over epsilon 2 is put into V1 and this will be reverse square square. Now that the transmittance is V2 1 square square simplified this have the transmittance 4 V2 upon this is the transmittance antiquate. Okay. Now the next question is like if you have calculated the okay, so we have calculated the reflectivity and the transmittivity. Transmittivity and this is This is the reflectivity. Transmittivity, here is the reflectivity. Now we know that whole thing. Okay. Now what we want to do is for next question. That is write down. Okay, that is what will be the value of R plus T at the interface. So they are asking question for it. R plus T at the interface. That means how much is being reflected and how much is being transmitted. If you sum it up, what will be the value? So here it is. So we have R plus T. R is V1 minus V2 whole square, right? V2 minus V1 whole square. Square over V1 plus V2 square plus 4 and V2 square plus V2 square minus 2 V2 V1 plus 4 V1 plus V2, sorry, 4 V1 V2, that and square of bottom one. Okay, same. So now you sum it up. So it will be V2 square plus V1 square minus cancel out and just take 2 and square that way at the interface the R plus T is 1. What does it mean? It does so this what does it signifies? So it signifies like how much is being transmitted and how much is being reflected. It is so this is the one if we started means if we are sending something at the interface and it has 1 watt of power. So whatever is will be transmitted and whatever will be reflected should be the sum of that power. The energy should not uh, disappear or increase or decrease. It should be constant and it should be one. No, not one. It should be conserved. So energy conservation is so from because whatever you're sending, whatever you reflecting, it should be the one. Okay, but you have normalized it with the incident energy, right? So that's why it should be one, the normalized one. And now the next question is prove that energy is conserved at the electric at the interface of an dielectric. So okay, so whatever I said, so this is the one. This is the value one. Now we have to elaborate it in more fine. Like we have to prove that energy is conserved at the interface. So we have what we have. So whatever you are sending the whatever the power you are sending through the incident, this half. So first write down the velocity. The medium. Sorry, this is the V1. This is half epsilon one and what and epsilon one and incident is well. Okay, so this is the total energy that you are sending through the media. Now, now what we have is the power you are sending through the incident. So again, keep this in mind. Now let us see what is the reflected power. That will be V1 half from one medium one because it's reflecting in the same media and FDR, right? And then we can write the transmitted one. This will be V2 because the media 2 half epsilon 2 transmitted square. Now what you can do, you sum it up, sum these things up, and we can check whether they are equal to this or not. If they are equal to, that means whatever we are sending, whatever is being reflected, whatever is being transmitted, they are in agreement. And that will show that this is the incident energy, this is the reflected energy, this is the transmitted energy. This two sum will give you this, and that means that energy is conserved. So let us sum it up. So we have this S R plus S T, that will be V1 of epsilon 1 I square plus V2 of epsilon 2 T square. But we know that ER and ET can be written in terms of EI square. So let's write that. So V1 epsilon 1 by 2 ER, ER can be written in terms of incident. So EI square, and that ER was V2 minus V1 square, right? Similar thing was V2 epsilon 2 by 2. The ET was written as 2. ET was like ET was, we can see, scroll. Okay, so ET was 2V2 over V2 plus V1. So what we can have is 2V2 over square of this and then EI square, right? Now we have to just sum it up. So what we can see, the things are common with this. So we have to take out V1 plus V2 whole square outside of the bracket. V1 epsilon 1 over 2 into V2 minus V1 square. And the EI square is common, both one of them. EI square taken out plus V2 epsilon 2 over 2. And then you have 4 V2 square. So uh, now we have to somehow prove this, that this is nothing but the energy that that is there in the incident wave, that is this. So what we will do for that, we will take out the V1 epsilon 1 square EI square is already outside. We are taking out this upon half, and this was outside already. So what will happen here? This will become like V2 minus V1 square, right? But what about this one? This will become half is taken out. So it will be like V2 epsilon 2 over V1 epsilon 1 and 4V2 square. Now to solve this, again we have seen that V1 N1 is V1, sorry, N1 is V1 equal to N2. That means that N1 is proportional to under root epsilon and V1 equal to this one epsilon 2 V2. And this is epsilon V1 square is equal to epsilon 2 V2 square. And that means that epsilon 1 over epsilon 2. So we have to calculate epsilon 2 over epsilon 1, and that is nothing but V1 over. Okay, so we can put it back here. So this is nothing but V1 epsilon 1 DI square 2 square. Uh, Now what will happen? This will be like V1 minus V2 minus square, and this will have V2 over V1, and epsilon 2 over epsilon is square. Square will cancel out this 4h here. Take this V1 will cancel out this. So it will be like V1 epsilon 1 pi square over 2 square. This will be like square this thing, square, this thing will be or this cancelled out. This is only one. This is more. Solve it out. Have this epsilon 1 pi square square. Whatever inside the bracket, this minus this plus, so it will become like this 4. So 2 is the square plus 2 and now it's simplified. So you have this ER plus, sorry, this is SR plus ST. Sorry, so you can simplify this as SR plus ST. Now you have this, so you have this, and then submitter P1 epsilon 1 square 2 square, and now you have this. So it will be cancelled out. And you can see indeed whatever whatever energy we have sent, that energy. Right? So this is the energy conservation at that. So now let's go to our next question. So that prove that the energy scattered at the interface of dielectric, we have proved that. Next question is, first we have to see what is the Poynting vector. So the Poynting vector denotes the flow of energy in the system. That we have already seen. Just want to recap. E cross P over mu0. The dielectric media is E cross H over okay, 20 is H. This was there, but already we have used it. So no need. But you know that the Poynting vector is what multiplied with the velocity in that media. If you take out the average, so we get the total energy that is flowing, so flowing per unit time, per unit area. So that is the power you are talking about. This is what gives you. And from here we can see that it's conserved for at the dielectric boundary. The key thing to notice is that the dielectric boundary is lossless, means whatever the power is coming is either being reflected or transmitted. There is no kind of absorption in the boundary itself. There can be some boundaries where there will be power absorption, and if there is so the physical understanding of that boundary can be heating up of the boundary. So if electromagnetic radiation is being partially transmitted and partially reflected and being absorbed, so that absorption can be seen as the resultant temperature. So overall, the energy is conserved, we can see from. Now, what we have to do, we have to look up for this next one. That is our next question. So we have a light incidenting on dielectric media of two interface with refracting index of n1 is equal to 1.5 and n2 is equal to 2.0. So now derive the time average Poynting vector components for both reflected and transmitted waves. So So he's saying, okay, and also prove that energy conservation holds at the interface, right? So let's say whatever the incident is EI amplitude of the incident wave. Now we know that the time average component of the reflected one was V2 minus V1 over V2 plus V1 square into EI square, right? Okay, now we also know that V2 is okay, so velocity inside any medium is C by M. So M is nothing but C by V. So this we can write here. We can substitute it here. So it will become S R. So it will be C by N1, N2 minus C by N1 square over C by sorry, sorry, sir. C by N2 plus C by N1 whole square. Now we have this. You can calculate N1 minus N2 over N1 plus N2 square, and you can take out the C from here and C from the bottom. So you have N1 plus N2 over N1 into N2, well, this term will cancel out with this one, this one, with this one. So in terms of, and the EI will be the same as have the SR in terms of the refractive index. It's N1 minus N2 over N1 plus N2 square square EI square. So this is the incident one. Now calculate calculate this. Uh, so we have this. Okay. So we have been given the M1 is 1.5 and M2 is 2. So it will be like 1.5 minus 2.0 over 1.5 plus 2.0 squared and squared. It is around zero point 0.5 squared over 3.5 squared. And then we have the reflex transmitted one, that is ST. ST is in terms of this refractive index is given as so in terms of refractive index, it will be can substitute it and we can check it out like what it can be. So for that we have to this was like 4 we would be 2 square I square, right? So that we have seen that I'm talking about the transmittance and the reflectance. See that is a 4 we will be 2 over square. So and this is not EI square. Sorry, this is the I made a mistake. So this is not correct. This is like it's correct partially because you have to just this was the only the electric. So you have to also multiply with the velocity in that video and the half factor and then epsilon one. This will give the energy density. This is the that will multiply with will give the power. So that's goes same for this one also. So it has to be multiplied with half epsilon. These are the things. So uh, but whatever irrespective of this, you can calculate this. Okay, but I think we don't need to do this all this math. Because what we can do just we can use the previously derived formula watch. Previously that we have derived was this one. Okay, so E1 half epsilon one E1 is square. But before deriving that, derived for substituted it all. So we can let's say that uh, we have to somehow show that reflectance and transmittance are equal to 1, and that means R plus T is equal to 1, right? So for that, we don't need this. We know that reflectance is V2 minus V1 over V2 plus V1 whole square, and the transmittance is 4, right? This is one. you write this in terms of n c by n1, c by n2 minus c by n1 over c by n2 plus c by n1 square have c square common. So n1 minus n2 over n2 n1 squared, again c square common here. n1 n2 over n2 n1 squared will cancel out this. Okay, the factors you have is n1 plus n2 n2 n1 whole square. So in terms of the now calculate the transmittance is n4 c1 v2, that means n by sorry c by n1 c by n2 upon v1 plus v2 means n c by n1 c by n2. So that means it can be simplified with 4c square n1 n2 and n1 plus n2 whole square into n1 n2 whole square here, because if we simplify this and c square will be taken out, so it will be like 4 n1 n2 over n1 plus n2 whole square. This is transmittance. Now let's put the values here. So 1 point what was question was like 1.5 1.5 plus 2.0 sorry 1.5 sorry here minus 1, some mistake here, wrong, plus and what sorry minus here plus 2.0 squared 0.5 squared over 3.5 squared. Okay, and this will be 4 into point 4 into what 1.5 and into 2 over 1.5 plus 2 squared. So we can just check it out. The reflectance will be like 0.5 squared over 3.5 squared. That will be just do calculation. You can find it out. Find it out as 0.5 and then we divided by 3.5 again. So it comes around 0.0204 converted to percentage value. So it will be like 2%, 2.2%. The transmittance will be 4 into 1.5 into 2, sorry, into 2 3.5. So it's around 9, 0.97959 something something. So it's like uh, we can take 3 decimal places only 1, 2, 3, 4. So it will be like 2.9. This will be 10. So it will be 8, 980. So if we take like this, so it would be like around the percentage value. So if you sum it up, R plus T, sum it up, it will be 100%. I've left some guesses there, but you can see that it's 100%. Okay, so the reflectance and transmittance are 100%. So and I told you that holds at energy law holds at the interface because this is that R plus T being 100% or 1 denotes that the energy is conserved. Question number 7 is a light of wavelength lambda 500 nanometer is normally incident from N1 equal to AL means 18.2 to dielectric with N2 is equal to 1.8. So they are asking like what will be the expression of transmitted intensity in terms of incident intensity I. So intensity is nothing but the I is the electric field square. This is the intensity. Okay, this is how the intensity is defined. So we have seen that the SR. Oh no, so this is the intensity. Right? Now what do you want to do? You want to calculate the intensity IT. So it is the II. So EI IT will be okay. This is how it will be. Now what you want to do? What we want to do is to calculate the IT in terms of II somehow. So we know that EI, sorry, ET was called the first question that we solved that ET was 2V2 over V2 plus V1 upon EI. So we are talking about the intensity. It's very simple. We have to square both sides. Square so V2 1 squared 1 and this is squared 1. So this is the IT. This is the 4V2 square over V2 plus 1. And this is the ER square. Okay. So this is the okay. This is IEI squared. II. So IT is in terms of II. So this is the coefficient have that relate the I this one. Now we have been given the refractive index that means N1 is 1 and N2 is 1 point. See what how much it is. So 1 to 1.8, 1.8. But we know that V2 is nothing but C by N2 and V1 is C by N1. So we can write IT in terms of N1 and 2 like C square by N2 square C by N2 plus C by N1 squared and II. So here you can have 4C square and N2 square C square. Take it out and square is N2 square over N2 and this squared. So this II C square is 1. This will go up N2 square and 1 square N2 square. Like the denominator we have N2 N1 square plus N2 square. Cancel out this. this plus n2 is the one square inside the this go like this. So it's n2 whole square and already we have there. So it will cancel out and it will use this. So means that IT we have 4n1 square equals n2 square I. Now we can put 4 1.4 8 I 12 I. So we can check it like how much is being how much intensity is being transported. So that will be calculation. It will be like 4 divided by 2.8 and then 8 divided by 2.8. This is around 510 around 51% transmitted. So it's not very transparent media. It's a half of the light is okay. Now the next question is so that the sum of reflected and transmitted power is equal to the incident power, i.e. R plus T is equal to 1. So verify this relation by explicitly calculating the reflectant and transmittant for the case of light from this to that. So we have already calculated something like this. So where we have to just change the N1 to N1 to the air, it's 1.2, and to the diamond 2.3. So very high reflectivity. Other metal is 2.4. So that's light very much. So that's why diamond is very expensive and it shines so much. So okay, so let's calculate this. So first we have to calculate how much is the transmitted intensity, how much the reflected one. So first let's calculate the coefficients that are 2.4. So the reflectance will be n2 minus n1 whole square. This will be n2 plus n1 whole square. We already denominator here is plus. So we just put the values 1.4. Sorry, this was 2.4 minus 1. 2.4 plus 1 is squared. This is squared. This is 1.4 squared. And this is 3.4 squared. So we have this. Can calculate this. And 1.4 1.4 divided by 3.4 divided by 2.4. It's around 1.6. So it's 0.1695% or 16.95%. Transmitted will be we have seen that in terms of refractive index is what was the formula? We can go back and check. So transmittance was the 4 and 1 and 2 over m1 plus m2 square. So you have to just write it down 4 and 2 plus m2 square. 4 for the diamond. So we have 4 squared so 6 divided by 3.4 80, sorry, 80 is some jump plus T, so it will be like 16.95 plus 83.4. It's around, I have replaced the one decimal place, so it will be around 5 also. See it, because I have not written the significant digit that was 0.9. Approximately you can write 0.5, 0.910, which is 0.9, and then 1 is here, 10, 9 is 10. So it's like 100%, whatever was being transmitted. Means this is the incident power. What we have plus T. So you can see that sum is 100%. So that means the energy is conserved, and because the condition for energy conservation, right? The reflectance and the transmittance of the incident power, how much is being transmitted and how much is being reflected. Now let's go to next question. That is reflection coefficient of a wave with transmission coefficient 0.35 each. So we know that it's very simple question. So we have the transmission coefficient is equal to 0.35. So I think it's very easy to solve, but since it was there, so we can see that the energy conservation demand that we are plus 1. So if T is given 0.35, then R 1, reactance will be 1 minus 0.35. And that means what? That means that like 65.65%, right? The reflectance. When the surface is very reflective, even though like the reflection is 0.65, so it's majorly reflecting surface rather than the transmitting surface. Okay. Now the next question will be uh, that the question is the incident wave amplitude shows 24 units. Amplitude incident, that means I 4. So reflected wave amplitude, the reflection coefficient is 0.6. So reflection coefficients are 0.6. So what will be the reflection wave? The reflection coefficient is this. So we have seen that we have seen that the ER square was so we have seen that the coefficient reflection coefficient is this, right? This is the reflection coefficient. So if this is the reflection coefficient, then what does it mean? It means that okay. So, reflection coefficient was n2 minus n1 over n2 plus n1 whole square, and then you have the what? You have the incident. So okay, no, sorry. So first let us write the reflection coefficient, that was n2 minus n1 whole square plus n2 over n2. So this is the reflection coefficient you have. And also you know the relation between the reflected amplitude and the transmitted one. So E0 I is something here. So that's something we have seen from the first equation. It was given like when we solved it for the first time. So we have this R is equal to V2 minus V1 over V2 plus V1. So that means and then we take out the square of that in terms of n1 and n2. So we see somewhere around somewhere around here. Okay, it was V2 minus V1 over V2 plus V1. And we calculated out it was N1 minus N2. So that means if this was like V2 minus V1 equal V2 plus V1. So this was that. But if you take out the square of both sides, so V2 minus V1 square square both sides have square. So, but this is the reflection coefficient that can be written like this with the substitution and so we know that we can directly write like this 1 minus n2 whole square over n1 plus n2 whole square each incident of square this. But we know this because we have been given that is like 24 square this because the unit we have given is 24 and this is like going from the reflective index are 1 and the reflective index the reflection coefficient is 0.6. So this coefficient this whole thing is 0.6 right each r squared each zero r the reflective index under root of zero point 0.6 into 4 squared. So we can calculate it very quickly so that we have multiplication of 0.6 with 24, 24 and then we can take the 0.6 so it's 24 squared right. Six that we have to take care of 0.6 so this much and we have to multiply it's around 18 EOR around 18.59. This is how much it will be. So the surface is like 24 inches, so 63, like around 75% of the incident line. Okay. Now the next question is so the reflection coefficient of a traveling wave through the media has a permittivity of 4 and 9. So calculate the reflection coefficient. R that what we have studied N1 minus N2, N1 plus N2. So you know that you have to calculate the reflection coefficient, but we know that N is proportional to under root of epsilon. So we can write it down here. N1 is under root epsilon 1 minus N2 under root epsilon 2 over under root epsilon 1 plus under root epsilon 2 squared. So we have 4 and 9. That means under root of 4 minus under root of 9 upon under root of 4 plus under root of 9. You have take by square here and here. And it's 2 minus 3 squared over 2 plus 3 squared. So you have 1 5 squared and it's 25. And if you take it like this, so it will be like 0. And then again, decimal uh, 0 here. So then you take one more 0 and the 100 it's like 0.04 like this. So 1 over 25 is 0.04. 0.04. So reflection coefficient is 0.04. And if you convert it to the percentage, so what was I would say like this was your question. So you can do it like this. If you convert it to percentage, it will like we have now covered all the things that we were supposed to do. So let us now conclude. So whatever we have done. So I will quickly go through this and tell you about the important points. So first we have this boundary of the dielectric where you are interested, like whatever the incident is coming, what is happening to that in the boundary, it is going to be 100% going or some part of it back. So we have seen that it depends on the materials dielectric constants, epsilon 1 and epsilon 2 ratios that we can see from here because the velocities that are there, velocity is proportional to c by n. Know that the n is nothing but proportional to the dielectric constants. So indirectly, what I'm saying that these coefficients, these things are depending on this little value as dielectric constant. Okay, and if it is so, so if I put like epsilon two, epsilon two is equal to epsilon one, when both the medium are same. So you can see that this reflected will be zero and the transmitted will be 1. That we can see from here. So that epsilon 2 is epsilon 1, that means V2 is equal to V1. For the variable C by V is same, right? That M1 equal to M2, so both media will have same velocity. So you can immediately see that this is 0. But you can see from here that this will become now twice of V over uh, twice of V down. Both, this is 1 and this is 0. That means what it is saying that all the amplitude that were incident is being transformed into the forward direction. And here also, it's saying that all the amplitude that were incident is not reflecting because you see the medium is same both sides of the boundary of your conceptual boundary because there is no actual boundary between same media, right? So this conceptual boundary that you have, same media, so all the light will be transmitted. Not nothing will be reflected from this virtual boundary that you are creating inside your mind. But if this is the dielectric media and this is the air, so it is a real boundary. So there would be this calculation that you have to do to get the actual reflection and transmittance of the light. And then we have calculated the energy density that was given by in terms of this S parameter. So yet this taking the average time average of S will give us the energy density and then multiplied with so energy density multiplied with this velocity will give us S parameter. That's the energy density. That's the power that is being carried by the electromagnetic waves. So that means if I'm giving some power, means I the incident wave has some power. So if it is being reflected and transmitted, so whatever the initial power was, given the condition that the media is not lossy, the summation of the transmitted power and the reflected power will be equal to the uh, incident power. And this is what we have proved here. We have first calculated the reflected, transmitted, and then we calculated in more detail. And then we found out, okay, this is the incident power. So first we take out the ratio to calculate the reflectance and transmittance. And then we have calculated this. Then we have to prove what is the R plus T. So we have done that also. So it actually comes out to 1. Then it was the energy conserved. So here we have shown the proof that SI, SR, ST. So SR plus ST should be SI, means the reflected and transmitted power should be equal to the incident power. So we have this here. So we can then do this, all the calculation steps, and finally we were able to show yes, indeed, the SR plus ST was SI. Okay, so this was we have done. Now, after that, calculated did some numericals where we proved that R plus T is equal to 1, or we have calculated the reflectance and transmittance coefficients, and then we prove that R plus T again there is 100%. This is again some miracles based on the question. But if you have understood the concept, then you can clearly understand that what does it mean to uh, have a boundary, and if the incident is reflected back and transmitted, how much will be reflected back and how much it will be transmitted. So all these things you can know very easily because now you have this Maxwell's equation at the boundary. So from there you calculated the boundary conditions that should be satisfied, and from there then you found out that yes, the parallel components of electric field should be the same, and the perpendicular components of electric field. Okay, the parallel. So light is going in that direction. So all the parallel components in this area of the boundary or this area of the boundary, left hand side or right hand side, this would be equal. Similar for the magnetic field, that is and the propagation direction like this and this and this side also. This parallel components will be equal. And from here concluded that we calculated the reflection coefficient, the transmission coefficient, and from there we also calculated the reflectance, transmittance, reflectivity, transmittivity, all these things, whatever. All. So we have calculated all these things, and with that we have also calculated how much the power is being transmitted and reflected. And so this was our recap what we did today. Now with this, I would like to, if you, I would like to see the last slide. Okay. So with this, I want to acknowledge Professor Manoj Kumar Habula from IIT Kanpur, NPTEL team, PMRF team, and Department of Physics, IIT Kanpur. So the Department of Physics and NPTEL and PMRF team and Professor Manoj Kumar Habula has given me such an opportunity to conduct this problem solving session. Uh, and okay, and I want to make an one announcement, like not announcement, it's a regular announcement that I will be uploading this videos on YouTube where you can see them later on, and I will upload this presentation in the Google Sheet that has been shared with me through NPTEL, and you can see these slides there, and you can see these lectures on YouTube, and you can solve the question based on you can solve these questions for practicing your assignment problems. So we will uh, solve more questions in the coming weeks. Okay, so I will see you in the next week.